Bonjour, Marc.
English, please.
Of course. How are you, Marc?
I'm good, thank you, Harold.
So we are here at VeriQloud. I'm Harold Olivier. I'm a researcher at INRIA, and I'm working in quantum information processing since 2001. And I'm here to visit VeriQloud and hear about Qline.
Hi everyone, I'm Mark Kaplan. I'm the CEO, founder of VeriQloud. VeriQloud is a startup. We are based in Paris, and we work on quantum communication. The purpose of the webinar today is to demonstrate our technology and our technologies, I should say. So first, let me thank Harold for being here and presenting with me. Thank to all of you for your interest in our technologies. Just a few words before we start. You can leave comments in the chat. If we have time, we will try to answer questions at the end of the webinar. And of course, the replay will be available. So if you're interested in sharing this video with your colleagues, it's of course possible as well. So let's start and talk about us.
Yes. So, what are the technologies that you are developing at VeriQloud?
Yeah, just a second. Go ahead. So at VeriQloud, we work on. Oh, we have a problem with the sound, I was told. I don't see it. Okay, it seems okay. Sorry for that. First, this is our first webinar online, and we're still setting up all the technical aspects. So yeah, at VeriQloud we work on quantum communication, as I was saying. So we founded VeriQloud with my co-founders Elham Kashefi and Josh Nunn, because what we wanted to do was to develop more and more applications for quantum networks. And we have this view for short-term, mid-term, and long-term. Especially so in the short term, what we do is more related to QKD networks and applications for QKD networks. And we have a roadmap of applications and technology development that goes all the way to the long term. Long term being connecting quantum computers to quantum network. So today, the purpose of the technology is to present what already exists. Not research projects, but the technologies that we have already developed that are related to quantum key distribution networks with applications.
So what kind of products are you going to present then today?
So the first product that we are going to present is called the Qline. Qline is a network architecture that aims at solving the last mile problem of quantum networks. As we will see with Qline, the main asset that we have is not really on the physics, although it's a hardware solution, but it's on the architecture, how we assemble things in order to solve the last mile problem of quantum networks. And the second product that we're going to present is HiCloud. HiCloud is a software solution that runs on top of Qline. And the purpose of HiCloud is to ensure long-term security, but this time for storage. So these two products, we will present first the theory, but also how it works in practice, starting with Qline.
Yeah, sure. So what's the concept behind Qline?
Okay, let's use the board here, and I will present you how it works. So before I start, let me just remind you a little bit about how quantum key distribution works. So in quantum key distribution, you have two parties, Alice and Bob, and you have Alice generates a quantum state that is received by Bob. Bob measures, and the physics tells us that this is a random shared bit. If Eve in the middle tries to read the bit, or read the quantum state, the qubit that goes from Alice to Bob, then the quantum state is changed, and Eve will get caught by Alice and Bob. In Qline, we do something something to scale a QKD network, which is on this poster here. Can you please zoom? Yeah. Thank you. So starting from the same pair, Alice and Bob, where Alice generates quantum state and Bob measures quantum state, we add in the middle these intermediate nodes, Charlie 1 to Charlie n. And what the Charlies are doing is just modulating or doing rotations on those quantum states to change their state. It turns out that this is sufficient to exchange keys between any pair of nodes of the network. Right, so now you realize we started from QKD, which is just a point-to-point solution, and we scaled it to a network solution, a fully connected network, actually, solution using just these intermediate modulators. And this has two advantages. The first advantage is that modulating quantum state is very easy. You can do it with off-the-shelf telecom components. So it does not require any specific quantum information processing hardware to do so. And the second advantage is that, well, if you have a QKD network that is point-to-point and you want to scale it to multiple nodes, you might need to route the keys throughout the network, right? In QKD, you just establish keys, so you need to route those keys, and those keys appear clearly to intermediate parties. With Qline, there is no such problem. You don't need to route the keys. Any pair of nodes here, Alice and Charlie n, Charlie 1 and Charlie n, or Charlie 1 and Bob, can establish a shared key. So overall, I like to say that Qline achieves a different trade-off between security, cost, and performances compared to QKD. And the reason I like to present it as the last mile solution for quantum networks is because the drawback or the counterpart of having a fully connected network scaling with telecom components is the following. Where in QKD you have, let's say, roughly 100 kilometers between Alice and Bob. On Qline, you will have 100 kilometers for the whole network. So the goal is not to scale something at the scale of a country. The goal is to scale locally at the metropolitan area space the network.
So if I understand correctly, basically you have just a single fiber between Alice and Bob, and in spite of this, you are able to generate a complete graph of connections between parties sharing keys.
Yes, so you can share keys between any pair of nodes in the network. The physical components, as I was saying, are very, very standard. It's what you have at Alice and Bob is exactly the same as any QKD hardware. And a Charlie node is just only has this phase modulator to change the quantum state of the system that goes into from Alice to Bob. Just as a reminder for the people that are not so familiar with QKD, the connection between the different nodes is a completely standard optical fiber, 1550 nanometers, so it's compatible with the fiber that is deployed today in any country in the world.
Okay, so and does this theory turn into practice? Like, do you have like devices that do this?
Yes, sure. We have developed devices, so I invite you to go and visit our lab to check by yourself, okay. And we will show it to the. I will switch the camera so that we can see the lab.
Okay.
Okay. And then you can come back here.
Yeah, sure.
See you in a minute.
Hello. Oh.
Hello. We have our hardware.
Yes.
This is the.
Okay.
So what you see in Qline, we have 4 nodes, Alice, and we have 2 Charlies. Charlies are just modulated only nodes,
Okay.
and we have.
Okay, so that's when we see the poster showed us. So that's the line left.
Yeah,
This
this is one.
right.
You can see only one fiber.
Okay.
To connect all the nodes together with the quantum communicators.
Okay. So basically, so the photon is from here down to this first later.
Yes, exactly.
To get here,
Yeah.
then.
Yes. So Alice is the sender, coder. She has 1 nanometer laser. Then you have only Charlie. They only modulate the phase of the photos, and Bob has his own interferometer and his own signal detector.
Okay. So what is the rest? Like all the equipment on top?
Yes. So the white boxes are the commercial microwave switches. And we use them to distribute the same clock to every node for synchronization.
Okay.
And the small black boxes are the servers. They are the MUX systems, which we use to control all the hardware parts.
Okay, so if I understand correctly, basically this is really like the hardware that you need. This is the quantum part. This is just the classical signal.
Yes.
And this is like the application would probably sit.
Yes,
between
the
these
interface, the user interface.
Okay.
Yes.
Okay.
So the whole this is Alice. So Alice is this box with the white rack switch and the computer on top.
Okay.
Yes, exactly.
Some more to see?
Well,
What you can say more about our hardware?
I don't know. This the hardware. Yeah. We have some interface for monitoring up there that shows qubit error rates.
Okay.
Currently, well, I think we are currently it's running on the simulator. Actually, even though the system is on, but just 10 minutes before the demo we had a little hardware problem. But you wouldn't see any difference. Normally we have a qubit error rate around 4% in the system, and everyone's generating keys at a couple of kilobits per second, like 3 kilobits to 10 kilobits, and that key is stored in a KMS, and then the user can either collect that key or can do some stuff with it.
Okay. So I think I'll go back and continue with Mark. Now that you see that the device is operational and actually like not so complicated, I guess I wouldn't try to do it myself, but it looks like relatively standard.
Absolutely, especially the optics part is standard telecoms components. The electronics hardware we develop ourselves, which includes an FPGA and the clock synchronization on the hardware level. So it's fairly standard compared to quantum optics level to see sometimes.
Okay, thank you.
You're welcome. Thank you.
So it was very nice.
Thank you.
But is that only existing in the lab here, or did you already deploy it somewhere? Is it used?
We have indeed deployed it. You can see the results here on the graph. If you can zoom. This is the result of a deployment that has happened at Deutsche Telekom. We have deployed it on the OpenQKD network. The results are in the poster, but probably more convincing for the people that are watching. There is a link to the paper in the description of the video showing exactly those results over time. Just before we move on, I would like to show the interface on my computer, because unfortunately we were not able to plug that interface to the real hardware, but I can show you how it works on the simulator. So it's here. You can see the interface to monitor the Qline in general. With here the quantum bit error rate for each pair of nodes of the network. The error correcting code efficiency, which is not very relevant like this, but if we look at a specific node, then we see it varying over time. And here the secret key produced for each interval of time. This corresponds to a very specific scheduling here, where you can see Alice establishing nodes between herself and Bob, and then Charlie 1, and then Charlie 2. and so on and so on. So Alice is involved in all of the key establishment processes, but it's very easy to change the scheduling. And for example, just by a few command line, you can switch it to exchanging keys between all the pairs of nodes in the network.
Okay, so here you like talking about the network topology of who is sharing keys with who. Here you have a sort of star graph where you have Alice and establishing keys with all the others.
Absolutely.
Okay, and then what you can do is change this configuration to change like to complete graph
to a
or
complete
anything.
graph.
Okay.
Absolutely.
So that's nice because then probably I guess you can vary the applications and the usefulness of the deployed infrastructure.
Yes, absolutely. In fact, this scheduling, again, I was telling it runs right now the interface on simulation mode, but it's the same with the real hardware. For the scheduling, the scheduling corresponds to a very specific application that we are also developing, which is iCloud.
Okay, so what is iCloud then?
So let me show you here. I have a few slides this time to present the application. The idea of iCloud is that you can use quantum key distribution in combination with classical cryptography to ensure not only the security of communication, but also of storage. Mm-hmm. And by this combination, it's not something that we have invented. It's actually public research. By this combination, what you get is all the advantages of quantum cybersecurity, not for communication, but for data at rest or for storage, right? So these advantages are, of course, everlasting security. It's long-term security, right? Remember that quantum is the only way to guarantee security in the long time. And the main ingredient that we need for that on the classical side, well, on the quantum side, is just quantum key distribution. So it's what is available today for quantum communication. For the classical part, the type of security cryptography that we need is a secret sharing scheme, right? So by using a secret sharing scheme, what you can do is ensure at the same time privacy, availability, and integrity, which is exactly what you want for cloud security in general. And the way a secret sharing scheme works, I won't go into the mathematical details here, but you can think of it as a polynomial. For those of you who studied math, you might remember that if you have a number of points in a polynomial, if you have enough points of the polynomial, you can reconstruct the curve exactly. And this is exactly the same here. What we want to do in order to ensure the security of storage is to split data on several servers. Here I have an animation. You split the data and you distribute them on several servers. And the type of security that you get is that each server here contains some data, but if it leaks, it's not enough to reconstruct the original secret data that you've been storing, right? So in order to attack or to learn the secret data, an eavesdropper would need to attack several servers and get the data from several servers. I like to think about it as exponential security because what it means is that in order to learn the secret data, the eavesdropper needs to break several security measures and not only attack the weakest point of the system. Usually we say that security is at most the security of the weakest link. With secret sharing, what we can have is multiply the security measure and hence exponential security. And last but not least, when we add the quantum magic to it, what we get is exactly what we want, meaning that we have stored the shares on several servers, and we can go further and renew the shares. And by renewing the shares, what we get is the strongest possible security, meaning that in order to learn the data, the eavesdropper needs to attack several servers all at the same time. Not only one, but all at the same time. This is something that has been, as I was saying, it has been proposed by researchers from academia. You see the paper here. It has been also implemented on QKD network. The only thing that we are pretending is that Qline is very well suited for this application. The reason is that it corresponds very well, it fits very well with the idea of cloud availability zone, which is exactly at the right scale for us, meaning it's metropolitan area scale.
Okay. And so, do you have like an implementation of this protocol and this application?
Yes, sure. So let me maybe call my colleague Clément to do the demonstration. He's the lead developer of iCloud. So iCloud, again, is the combination of QKD or Qline with secret sharing.
Hi. So we'll do a quick demonstration of what we can do with iCloud. So here I have the interface, and so we can see here we have 3 servers on which we will distribute the file we want to protect. So let's choose files. We choose to upload a prescription and a customer database. The files could be sensible. Here is the protection of the prescription with a threshold of 3, meaning that we will need the information of 3 storage servers to retrieve the information. So we're protecting it. And then we will do the same with another file. Let's choose this customer database. And we will put a threshold of 2. So we'll need only 2 servers available and at least 2 servers to retrieve the file.
So if I understand correctly, in the prescription case, what you choose is to maximize security?
Yeah, kind of. So for the prescription, we need 3 storage servers, meaning that if we just have 2 available, we won't be able to retrieve. This is the security.
So that's secure, but it's a little bit like...
Yeah. On the other end, for example, for the customer database,
okay.
If we have, for example, 1 server that is not available because of some reason, for some time, we still be able to retrieve it. So you have to choose the threshold depending on what you want to do with your files. Let's choose...
maybe just before you... Yeah. So if you had more servers, you could still choose a threshold of 3 or 4 maybe.
Yes, of course.
And then get both robustness on one hand and security.
Exactly. Okay. So let's do a quick demo. Let's choose randomly 1 server and simulate that is not available at some time.
Okay.
Asimov, Zamiatin or Barjavel, as you prefer. Okay, so let's switch off, let's say Asimov.
Okay.
Up. Just need to refresh. Okay. So the first storage, we stored it with a threshold of 3.
Okay.
And now we have just 2 storage available. We can imagine, for example, an attacker having access to the 2 servers out of 3. So we won't be able to retrieve the file because there is not enough storage server. But our customer database, we stored it with a threshold of 2. In this case, let's imagine that one of the servers is not available because the host has been attacked. We don't know. This one, we will be able to retrieve it. So here, it just appears, you have to trust us that the file is well uploaded. We didn't have any error and we could display it. Okay, on that, let's try to have Asimov back again. Okay. Let's say the connection is back. And we will be able to retrieve our first file without problem. And here we have the prescription that we wanted to store. And that's it.
Okay, thank you.
You're welcome.
So Mark, maybe it's time to round up a little bit about these applications. So what's the interest of already having products from VeriQloud now?
Let's maybe go back to the chairs. We can continue the discussion. Just before we do, I just wanted to remind everyone that you can ask questions in the chat, and we can answer those questions at the end of the presentation. Up, let's go. Yeah, so as I was saying, often quantum key distribution, when it's presented, it's for the security of communication. I believe that there is a great opportunity here to build a quantum secure hybrid data center. What we've seen with iCloud is that by mixing classical and cryptography and quantum cryptography, we can get such an architecture, right? And what we need for that is something that doesn't require more research. It's something that is already available. You need quantum key distribution hardware, such as Qline that we've presented, and you need dark fiber to connect the hardware together. And on top of that, you deploy a simple software software that we are developing to build such an infrastructure, right? So it already exists. Nevertheless, we know that for many, especially cloud providers, getting access to the fiber is not always easy. So one of the things that is possible, you can fully deploy the software part, the secure secret sharing scheme to distribute the data on a fully classical network. The way we presented it, as you've seen, we presented the interface in simulated mode, and Shamir secret sharing was also run in simulation mode on my laptop here. Right, so it's completely possible to deploy a quantum safe data center using only the software part of what we're developing, and then upgrade to quantum to get the best possible security for your data.
Okay, so basically what you are saying is you can explore everything, start integrating the solution without necessarily investing into the hardware part. Test that everything works as suited, and then when it's ready, then switch to the quantum part.
Indeed. So I spoke about how high cloud can run on a simulated network, but also you can run the key extraction interface in simulated mode, meaning that you can emulate a quantum key distribution network on a classical network. Of course, don't get me wrong, there is no security if you do that, but it means that you can start working on the integration using the standard APIs that were standardized at ETSI to work on the integration even before getting access to the quantum hardware. You're right. So you can start developing your own applications, how the keys can be used to secure your own application before getting the hardware, and you can start building quantum safe infrastructures for your data.
Okay, so you said, like, okay, of course, if I don't use quantum, then there is no specific security, or not more than possibly like the classical security that you already have. But how does the security go when you start and switch to quantum, actually? Like, is that something that you can certify, or?
Yeah, good question. So the certification processes for quantum hardware is only beginning right now. Right, so we've seen companies manufacturing hardware for a while already, but the first ISO norm is from last year, right? So it's very beginning. In particular, the hardware that we showed you earlier in the lab here is completely for demonstration. Right now, since it has been deployed, we are putting it into production, and I have one of the new boxes here that I wanted to present. Right, so it's very, very pretty, and it matches with the colors of VeriQloud, and it will be fully integratable into a data center type infrastructure. But there is not yet any certification process that is established for such a hardware, right? So it's something that needs to be discussed with every potential customer.
Okay, and so you showed like the new production box and device. So what's the future in terms of technology developments at VeriQloud?
All right, so as I was saying in the beginning, we started by saying that right now this Qline that we're developing is for quantum key distribution networks. Quantum key distribution networks, they are here. They have been deployed all over the world. You might have heard about China, which has the largest QKD network in the world, and you can use it for security. We know that this is a part of a larger group that we call quantum technologies, and in particular, quantum technologies contains quantum computing. And one of the things that we've showed last year, so this is more on the research part of VeriQloud, is that the exact same boxes that we are manufacturing, the Charlies that you've seen in the lab in the other room, they can be used for another task, which is secure quantum cloud computing. Okay, so what is secure quantum cloud computing? In the future, when we will have quantum computers, we will want to connect them to quantum networks, of course. And the reason for that is that it has been shown that if you can connect your quantum computer to a quantum network, you can, with a very light client, actually precisely the Charlies that we are manufacturing, you can delegate a computation to a quantum computer, but in a fully encrypted way. It means that the institution that provides the quantum computer doesn't learn anything about the data, doesn't learn anything about the computation itself or the output, right? We figured out by developing this, this technique, the technique behind that is called blind quantum computing, and I give credit for that to my co-founder, Elham Kashefi, who published the first full solution to this problem. What we've seen is that already today, when you are a bank, for example, and you want to produce a new or work on a new algorithm for portfolio optimization, banks are not allowed to use personal data. And there are good reasons for that. We can't change that. So computing, sending an encrypted version of a quantum program to a quantum computer is a solution to this problem. It addresses exactly this problem, and this problem already exists today. So just to summarize, what I was saying is that we have published a new research last year with the University of Rome showing that the exact same devices that we are manufacturing now, in order to scale up quantum key distribution, they can be used for secure quantum cloud computing. So this is where we see the future of VeriQloud, and this is how we want to go from the current situation to the longer term situation where we will have quantum computers.
Okay, so in a sense, what your roadmap is to make quantum computing secure and available to institutions that have very little quantum capabilities, and being able to do that in a secure and delegated way, so that they can access computers that are rented in the data centers. Basically.
Yeah, it's absolutely this. We all know about the limitations we have in data sharing. GDPR in Europe is very, very important. So all this class of cryptographic functionalities, they address exactly this problem.
Okay, thank you.
Thank you, Harold.
It was a pleasure to see the devices and have this presentation. Thank you.
Yeah, you're welcome. As you may have noticed, the YouTube channel is new. We aim at having more and more contents. Today it was a webinar to show our technology. We will probably have more webinars and more presentations in the future to demonstrate more use cases and the research that we are performing at VeriQloud. So if you want to follow them, don't hesitate to register to the YouTube channel. There is a question in the chat. Okay. So I'm thinking, since we have time, so there is a question by Axel Ferrazini. If there was one technology that would need to be standardized by ETSI to enable better interoperability in QKD from the VeriQloud perspective, what should it be? I think the interoperability between QKD devices is okay for now, because what I was explaining in the beginning, when you start with a QKD device, it's only point-to-point. And if you want to scale it to a network, you have to add pairs of devices. The interoperability then happens at the software level between the different devices. And this is something that is well standardized, and most hardware manufacturer right now, they use the ETSI standard for that. Actually, in the implementation we did at Deutsche Telekom, it was almost plug and play. They could remove the hardware that they had from other manufacturer and put VeriQloud instead to test. Nevertheless, one of the things that we learned by just this very small change in the architecture, what we've seen is that one of the functionalities that was not an issue for quantum key distribution, and it becomes one for ours, is the clock distribution. So what my colleagues have shown you is that they use these white rabbit switches to distribute the clocks, because precisely we have the Charlies that don't have anything to measure, so they can't use the standard QKD techniques for that. So it is a problem for Qline, but it's also going to be a problem for future quantum networks. For example, if you have repeater networks. So repeaters are a piece of hardware that can amplify, so to say, the quantum signal. It's a very bad analogy, so don't repeat that. But the classical equivalent is to amplify a signal. In the quantum world, it's completely different, but it's the purpose is exactly to send a state from between any arbitrary node of the network without any limitation in the distance. And for this, you would need to distribute clocks between any pair of nodes. So I know that there are experiments to use dedicated network for clock distributions for quantum communication, but they are research projects, and it's not clear how the QKD people will use them in the future. So I would say that this is a very good avenue of research for not necessarily interoperability of QKD devices, but upgradability of quantum key distribution networks.
Okay, thank you. I think you have more questions.
Yes. We have a question from Daniel Holm saying, I assume that the modulator Charlie product cannot support entanglement-based QKD due to fundamental laws of quantum mechanics. I would rather say that at the moment it does not support. I mean, it's not made to support entanglement-based QKD, but what we know is that I mean, there's no fundamental laws of physics that prevents that. It's just not how they are made today. We don't have in our, so remember that the reason we develop such devices is because of their applications. And at the moment, we don't have applications for the Charlies with entanglement-based QKD, but it might change in the future. Okay, I think that's it.
Okay.
Don't hesitate to reach us at VeriQloud. Thank you, Harold,
Thank you, Mark.
for handling the presentation, and let me thank all the team, Clément, Eva, Georg, Faten, Hop, Lies, and all the other ones that are remote, and Eric, who was working on the production today.
Thank you.
Thank you.